We're now going to leave the kinematics portion of the class and head into the kinetics portion. So now we're going to go from the outcome of movement to the causes. We're going to do this to begin with from the linear component. Basic outline for this chapter is we'll just quickly discuss what force is, discuss the 3 Newton's laws, describe different types of forces that you'll encounter with human movement, and then we'll show how to implement these forces to the activity of interest using the free body diagram. So kinetics. So again, here we have the identifying the causes of motion, and it's a push or pull that tends to cause motion. Now, I've underlined, bolded, and italicized tends because just because it's a push or pull and a force doesn't mean motion has to occur. Here's a little diagram of a push or pull, and essentially here is a type of tug of war where you have tension in the rope. Gravity's pulling down on the rope as well as the individuals. Friction allows them to stay put while they're pulling. And then you have the normal force, which is opposing the body weight or going up. Now, interesting note is what I would like to point out to you is that the location of which they have drawn this normal force here is typically not where you'll see it. You'll typically see it coming down in this portion, and I can't draw right now, but going upwards. So imagine that was a straight line, right? And that's where you would typically see the normal force. Now, what are the characteristics of a force? There are 3 main characteristics illustrated here by the basketball shooter. The first is that it is a vector, so it does have magnitude and direction. Magnitude is represented by the length of the arrow, and the direction by way the arrow is pointing. The point of application is where you have the vector represented. So the point, generally when you're contacting with the ground reaction force we'll talk about earlier is the center of pressure. That's the point of application. But wherever the arrow is going from or targeting to, that is going to be the point of application. Oftentimes you'll see the GRF as I've drawn here underneath as opposed to coming out in a free body diagram. But as we're looking at it through real life situation, it would go up through the body like you see there. Towards the center of mass. And then you also have the line of application. The line of application is simply the path that the ground reaction force or the force vector travels. So here you have the line, and the point of application is where it is happening at the bottom. Now, it's very important to understand what the units are here, and those are newtons. Now, newtons are kilograms per meter, kilogram meters per second squared, right? So here is your acceleration component. And here is your mass component. So you have F equals ma. So there you have what your newtons are. So ma is kilograms meters per second squared. So one of the key components that you're going to need to know is you will need to know and be able to put in your own terms the 3 Newton's laws. I have read an interesting book about Newton, and some of the greatest people in the world were thought to be crazy during their times. But now remember, these are laws. And so Newton, and for the years leading up after his death and throughout the process, people have tried and tried and tried, or especially early on, to disprove his laws. At the time, they were theories. And then because nobody has been able to disprove them, they have become laws over time. But his first law is the law of inertia, law of acceleration, and law of action and reaction. And we'll go individually into each one of these and really talk about what it means. And we're going to try to do this from a human perspective, but again, remember, he's a physicist. So when they did this, it was really being done with objects in space and objects on the ground. So the law of inertia, this is Newton's first law of motion. It's the tendency of an object to resist motion, and the idea here is to resist a change in motion. So not just motion, but a change in motion from the current state. An object remains in the current state of motion unless acted on by an outside force, right? So I'm going to be continuing whether I'm stationary or moving, unless something does something else to change that in some force. So if I'm stationary, I'm going to be stationary unless I get pushed or wind comes along. And if I'm in motion, I will continue in that velocity unless something else comes to change that velocity. So let's talk about what inertia is, and that's the resistance to motion related to the mass of the object. So when you see inertia, relate it to the component of mass, because that's where it comes into play. Mass is our quantity measure of the amount of inertia in an object. Okay, so it's a portion of matter that allows the object to remain in that current state of motion, whether it's going to be stationary or in motion. Okay, so let's think about how that works and how objects of greater mass require more force to move, or greater mass are more difficult to move. So now I wanted to give you some images relative to a soccer ball and how that represents Newton's first law. In image 1, you have a soccer ball that remains at rest. It's sitting there before the game starts in the center line, and it's going to sit there until an outside force comes. Now, if the wind's blowing that day, the wind can blow the ball, and that is a force. Or what happens is you have a soccer ball player in 2 that comes up and puts some force through impact on the soccer ball, which creates some kind of flight path. And at that point, you know, from previous lectures, that it becomes a projectile motion, so it leaves the ground if they put an upward trajectory of it. And from the look of the foot here, I would imagine that that ball would travel in the path that you have over here. And that becomes object in motion. Okay, and another thing you know about projectile motion is in the horizontal, we're going to pretty much remove air resistance, although this ball will spin and there's other things happening. But in the vertical motion, you do know that there is a force acting down on it, and that is the force due to gravity. So this law of motion says that the ball will remain in this upward trajectory unless there is an outside force. In this case, there is an outside force, and it's a force of gravity. And that is why the ball does not continue to travel upwards. Instead, it's going to go up to a high speed because gravity is acting on it, an outside force, and pushes it back down. In the horizontal motion, here we have in situation 4, where it went to the back of the net. This person scored a goal, and so the net is a force that is acting backwards on it, and we can call this the force of the normal, or we can call it force of the net, whatever you want to call it. And I call it a normal force because it's going directly back towards the ball. So we can, you know, talk about outweigh each way, but you call it force of the net really, and it's a deceleration or a stopping force that is causing the ball to stop in the back of the net. But as we go forward, I want you to think about sumo wrestling. And if we talk about what inertia is from the previous slide, if we talk about inertia as mass, then we can really think about what's happening with these sumo wrestlers. You're going to have huge masses, right? So if you ever watch sumo wrestling, it's one of my favorite things to watch. These guys are amazing athletes. You can see how this one, the one with his back to us, gets his body underneath the other one. And that's a leverage concept. But once he gets them moving, right, it's really hard to get people moving. If you see sumo wrestlers a lot of times they're slapping, a lot of times they're moving, and what they're trying to do is get the other person off balance because this inertia mass concept. Because if they're stationary with a wide base and their center of mass is really low to the ground, it's hard to get them moving. Their resistance to motion from a standstill is much more difficult. But once you get somebody off balance, like this guy facing us, and they start moving, now the inertia to stop the motion, it becomes more difficult. And now it's easier for this person to push him off or out of the circle because it's hard for the bigger guy, the guy that's out of balance here, to stop his motion. Okay, so this is where the idea is of inertia. Getting something to move is difficult, but also stopping something becomes really difficult as well if the mass is bigger in this situation. Moving on to Newton's second law of motion, we have the law of acceleration, otherwise known too as the law of momentum. We'll discuss how that is and why that's seen here shortly, but let's go first and let's talk about what the law of acceleration is. Definition-wise, we talk about an object's acceleration or the outcome of application of forces or the outcome of what we see, acceleration, the kinematic piece of this, as proportional to the resultant force in the same direction. And that is this part here on the left-hand side of the equation. The resultant force is essentially the sum of the forces in that direction. So if it was in the x direction, this would be x, and the acceleration of x. If it was in the y direction, it would be this way. And if it was in three-dimensional, it would be sum of in the z equals ma. So you see this subscript component means that we're breaking it down into all the components. Okay, so that's where the resultant force comes in. And then it's inversely proportional to your mass. Well, here you have your mass. So if I want to isolate acceleration, I have to divide both sides by m. So the m becomes over here, and so now a is equal to the inverse of mass. Okay, so that is essentially what this is defining into the equation. Now, it's going to be very important for you to memorize this equation. This equation is what we're all about, okay? And we'll talk about that more. But if I ask you to explain the law of acceleration for me, you can do it two ways, one of two ways. You can give me these two words or two phrases, or you can give me this and help this to tell me what it is, right? So this equation here is equivalent to what both of these are saying. Here's the kinematic piece. Here's your kinetic piece. Okay, so remember that with the arrows, what this is talking about is as force increases, the resultant force in the same direction proportional. So if I increase my force given by this arrow, then my acceleration should also increase. If I decrease my force, then my acceleration should decrease. Okay. Now, I will tell you there's times in human motion that this doesn't happen, and we can talk about that later on. But for a general understanding, there's a linear relationship between force and acceleration, between the kinematic component, which is the outcome, and the kinetic portion, which is the cause. So there's a linear. So now we're going to talk about an application piece of this. And so think about this. You have mass 1, and down here you have mass 2. Okay, so there's differences in mass. Now, if we want them to have the same acceleration, so if their acceleration is to be equal, which person 1 or person 2, do you think is going to need to have a greater force application? Now, you can cheat and look at their faces and understand which one has a greater force application on this. Or you can think about it. In order, if my mass is increased, and I want to have the same acceleration, well, we know which one's going to have a greater force application. Let me ask you this another way. Which one of these two objects, if both were stationary, has a greater inertia? Remember what inertia is. Inertia is resistance to motion or change in motion, represented in this graph by the mass part. So one is going to need to have a greater force application to produce the same acceleration. If I say this a little differently, I would say if they both had the same force application, person 1 and person 2, which person would exhibit a greater acceleration, which is what? A change in velocity, therefore a greater momentum, 1 or 2? And your answer would be 2 in this case. Because 2, if he had the same force application as 1, would have a greater change in the mass times velocity. Okay. Now, I just use that term momentum, and we've used momentum quite a bit in this class, and I don't know if everybody understands truly what it is. So I want to take this time to really go into how momentum is what he originally is. And momentum we're going to use as rho. So rho is momentum. Okay. So if we look at this, and we start with sum of forces equals mass times acceleration. If we bring this down on the left-hand side, it's going to be mass times delta V over delta T. There's our equation. Now, if I take this and I isolate mv, which is right there my mass times acceleration, my new equation is sum of forces equals change in rho, looks like a P, over change in T. So here is law of acceleration, Newton's second law of motion, written as law of momentum. It's sum of forces equals delta momentum, or delta rho, over delta T. And remember, delta rho is simply mass times delta V, or the momentum of the object. Moving on to Newton's third law of motion. There's two key words here that I need you to remember, and I need you to recognize that what the difference is. And I have them highlighted in red and underscored because, or underlined, because I might ask you this, okay? So the idea with Newton's third law is for every force exerted by an object, there is an equal and opposite force on the object. For every force exerted by an object, there's an equal and opposite force on the object. It's a very important statement, and understand where by and on are in this equation. So it looks like this in equation form. So again, Newton's third law, you can either represent it this way or this way. And what it says is for the sum of forces of A acting on B, or for every force, sum of forces exerted by A on B, B exerts the equal and opposite force, here's the opposite, here's the equal, on A. So we could change this by A by B equals the equal and opposite B on A. So if you want to change this in the equation, you can. But this means that A acts on B and B acts on A in the equal opposite way. And then I just do a little fun little comic book that I found online here that's going to talk a little bit about it. You can follow that through and have fun with that if you wish.